Lesson 6.3 is on linear equations and two variables. What we're going to do in this lesson is not anything new. Basically, we've done everything before, but what's new about it is how we're thinking about it. We've started the discussion on functions. We know that function means that for every input there's exactly one output. But what we also want to talk about is the different ways to represent these relations, and in some cases functions. What are the different ways we can represent them? So let's just start with a simple simple equation here with two variables, x minus 3y equals negative 1. We want to know whether some x and y values are solutions. Tell whether the ordered pair is a solution of the equation. Well, remember, our first coordinate is our x coordinate, our second coordinate is our y coordinate. We want to know if I input 4 and 2 into this equation, does it result in a true statement? Well, plug things in. Instead of saying x minus 3y, say 4 minus 3 times 2. We want to know, by inputting those two values, does that equal a negative 1? 4 minus 3 times 2 is 6. Does that equal a negative 1? No, it doesn't. 4 minus 6 is a negative 2. That doesn't equal a negative 1. Is this ordered pair a solution? No. Now let's look at 2, 1 here. Do the same thing. This is our x value, this is our y value. Input it into this equation. 2 minus 3 times 1, does that equal a negative 1? 2 minus 3, does that equal a negative 1? Yes, it does. So these aren't just random. We just don't randomly throw x and y's. We don't always use x and y's, as you're going to see in the next example, but a lot of times we do because our ordered pairs are x coordinate and y coordinate. So all of this is tied in. Graphs, x-axis, y-axis, ordered pairs, x coordinate, y coordinate. Usually equations using x and y. Okay, because they're all related, they're all different ways to represent a relation. Except in this case, we're not going to use x's and y's, we're going to use p's and d's. The number of pages p that Donald has left to write for his 30-page research paper depends on how many days d he writes 5 pages per day. Don't worry though, because it tells us that the situation can be modeled by the equation p equals 30 minus 5d. What does this mean? The number of pages he has left to write equals 30, that's what he starts with, minus 5 per day. Now the first one says make a table of solutions for the equation. So what you want to think about here is which one is your independent and which one is your dependent variable. Which one's your x, which one's your y. Looking at this, the number of pages we write is dependent on how many days we have. So let's start with days. And then that'll tell us how many pages we have left. Now, as I've mentioned in the past, I always start with 0. 0 is a good starting point. When Donald is starting to write this paper, how many pages is he starting with? So after 0 days, if I put a 0 in here, or you can just read it, there's 30 pages left. Well, after 1 day, you can put a 1 in here. 30 minus 5 times 1 is 25. After 2 days, you're going to start to see a pattern here. We don't necessarily have to go and put a 2 in for d. 5 times 2 is 10. 30 minus 10 is 20. We can see that after 3 days, if you notice, we're subtracting 5 each time. After 4 days, and you get the idea. Why would we do a table? A table is another way for us to represent this relation. This relationship between the number of days Donald writes and the number of pages he has. And a table can help us answer the next question. How many days does he need to finish his paper? Well, if we continue our table, after 5 days, there's 5 pages left. After 6 days, there's 0 pages left. We know that he needs 6 days. Another way we can do it, because remember, our function was given to us as equation first, this is a way we can represent the relationship between pages and days. And we can say, you know what, I want to know when he finishes his paper, he has 0 pages left. So I could just use the equation instead of making a table and say, okay, he's going to be done when he hits 0 pages. And then solve this equation, and what you're going to see is that we get the same answer. Negative 30 divided by negative 5 is going to be 6. So whether you use the table or use your knowledge of equations, those two different representations of the relationship give us the answer to the problem. Again, these are things we've done before, just different ways to represent them. Notice this one says graph y equals 1/2 x minus 1. Cool, slope-intercept form, we can graph this. But I want to take a step back. Before we learned slope-intercept form, we learned to make an input-output table. And then you said, well, that's not fair because you didn't show us a quick and easy way to do it first. Well, again, the reason for that is when we get into quadratics and more advanced level equations, we need input-output tables. But let's just look at how we can represent this as a table. If you remember, I had to use -2 to start, so I'm going to go 1/2 times -2. I'm going to write it as a -2/1 minus 1. These all cancel out to give me -1 minus 1, and I get a -2. If I input a 0, I get 1/2 times 0 minus 1. And again, don't stress out why I'm doing this. I just want to show you that we can represent functions in different ways. Again, all things we've done before. 1/2 of 0 is 0. 0 minus 1 is a -1. And 2. 1/2 of 2 minus 1, that ends up being 1 minus 1, not 0. So we get these inputs and outputs. And remember, these actually can be represented by ordered pairs. So this function here can be represented as an equation. It can be represented as a table. It can be represented as ordered pairs. And then let's go right down to it. It can be represented as a graph. My y-intercept is -1. My slope is 1/2. It's positive, so I know my line is going up. Rise 1, run 2. And when we look at this line here, okay, it's not going to be perfect, but we'll let it go. Look at the points we just came up with. -2, -2. -2, -2. It's on the line. 0, -1. 0, -1. 2, 0. 2, 0. Notice they all lie on this line that we use slope-intercept form to graph. Everything that we've been working on is related. Input-output tables, graphing lines, ordered pairs. They all are related to each other. They're all different ways to represent functions, to represent relationships. Just a couple more quick examples. We talked about horizontal and vertical lines. So when we see something like x equals 1, and we're like, wait a minute, we need two variables here, not in this situation. Remember, x equals 1, if you think about it, x equals 1, our x-axis is horizontal. That means this is going to be a vertical line. Remember, it's opposite. We want our x to always be 1. So if we draw a vertical line through 1, what I want you to see is if I pick points, for example, if I pick this one right here, this is the point 1, 4. This is the point 1, 0. This is the point 1, -3. Notice that our x values here are always 1. So even though there's one variable, we still can draw it on the coordinate plane, which is two variables. So x equals 1 is just a vertical line through 1. We can represent it as an equation, we can represent it as these ordered pairs, we can represent it as a line. Likewise, y equals -4, our y-axis is vertical, so our y equals line is going to be horizontal. And it's going to be horizontal through -4. And again, when we go to check this out, this is the point -5, -4. This right here is the point -2, -4. 1, -4. And what I want you to see is that our y value is always equal to a negative 4. And that's what this says right here. So again, the majority of this lesson is not new things. It's just looking at the things we've been working on in a way that to see that they're all related, that there's a reason we have all these different representations.